Okay, so thank you very much. I'm Francesco from Julia, and I did this work during a fantastic sabbatical at Northeastern, where I had the chance to work with some fantastic colleagues, Julia, Artyom, Benjamin, and Jan, and to actually meet and work with Jeff, which was great. So, subtyping. I'd like to start with something very simple, and I'll try to be more grandiose later on. So subtyping. Let's start with something simple. Let's ask Julia, which are all the methods of the star operator, okay? And this is what we get. Okay, simple. Yes, let's look at what we get. We get, some of them are actually simple. Take the first one. It says, we can multiply a number by a range. Yeah, nice. We can actually multiply two numbers by converting them to the same internal representation via the promote function. Great. And there is one more, which is more fun, that says, if you give me two numbers which are both either signed or unsigned, then we can use a native multiplication to perform the multiplication. So this is nice and simple. Of course, there are monsters hiding there. But the real question is, so you have this, and you have the simple one. And imagine that you write 7 times 6. The question I want to study is, how does Julia select which method she wants to invoke among these 180 different overloadings of star? Okay? So, simple programming question, useful for all programmers of Julia. You want to know what your language is actually doing. So, for this, we have to understand multiple dispatch. So, what do we have to know? Let's take just the simple ones to make the example tractable, okay? Imagine that we write times 3 4.0, okay? So the first argument is an integer, the second is a float, and well, here it is easy. There is just one method that can apply, which is that one that tries to multiply two numbers, because the second argument is a float, and you never get a float otherwise in the second element. Now, let's be more evil. Let's try to multiply two integers, 3 and 4. Now there are two methods that can apply. Of course, we can use a multiplication of two numbers, because 3 and 4 are both numbers, or we can use the most specific one that says, give me two signed numbers, and I can use a native multiplication. And the Julia design says, whenever you get this kind of ambiguity, pick up the most specific method, which is pretty much what you always want. Okay? So, rule of thumb number 1, Julia will always pick the most specific method compatible with the type of the arguments. Okay? So to understand what's going on with multiple dispatch, we have to understand 3 things. The type of the arguments, the most specific, and compatible. Okay? So the type of the argument is easy. Why? Because Julia always knows it. At runtime, it always knows what's going on. And you can actually query it. You can ask, which is the type of a tuple 3 and 4.0, and it will reply tuple int float, which is what you expect. And you can do the same with the arrays. And Julia knows that this is an array, and this is what you expect. So the type of the argument is easy. It means to define the two other words, most specific and compatible. Okay? Now these two words build on the very same concept, which is a concept of subtyping. Compatible is really just subtyping. Most specific is subtyping plus some extra funky heuristics to simplify your life. Okay? But it is still 95% subtyping. So in what follows, I'll focus on compatible,
in all the examples. Okay? So let's try to understand the subtype relation.
General intuition about subtyping. Think of a type as a set of values. The type
int denotes the set of all the integers. Okay? And think of the subtype relation as set inclusion of the supporting sets. Some examples. Int smaller than sign. Well, we take the set of all the integers, we take the set of all the signed numbers, and yes, the set of the integer is subset of all the signed numbers. Okay? By the way, subtyping is denoted with a funky small semicolon since when academic people started writing papers about subtyping. Let's take something slightly more complicated. Union int float subtype of number. Okay, let's interpret union again as set-theoretic union. So what do we have here? We take all the integers, we take all the floating point numbers, we make the union, we get a big set, and it is still a subset of all the numbers. So inclusion works, and subtyping works. Okay, now to make things fun, in some cases, Julia will depart from this interpretation, and it is where the fun begins. So how is subtyping defined? It looks pretty important for the language to understand what subtyping does. Okay? It is at the basis of dispatch. And, well, it is defined by a file, which is called subtype.c. This is just a bit. I couldn't put all the pages on the slide. And it is C code. Let's zoom in it. What do we have? This is for all X
subtype, and yeah, it looks like C code. And if you look closer, then we discovered that it is an algorithm using mutable state. And it uses recursion over two explicitly managed stacks. Okay, at this point, two recursion stacks plus mutable state is a good recipe for a headache. Okay? So, in turn, we have 2,600 lines of my take, hard to read C code. And maybe it is not just my take, because if you take all the GitHub commits to this file.
In 2017, we discovered that it has been touched by 3 people in the world. Okay, so what we did, you cannot reason about 2,000 lines of C code using mutable state recursion in all directions and so on. So what we did was to understand what was going on and transform all this code into this nice and small set of rules. And what do we have here? We have a specification of subtyping, not an algorithm, a specification of subtyping in a precise mathematical language. Okay? And this is what I'll try to, in the rest of the talk, I'll make a guided tour across these rules. I won't tell you all the truths, but I will give you the intuitions that will help you in your programming practice, and then there will be hints for the hardcore programmers if they want more. So let's try to understand subtyping. So those rules might look ugly if you're naive, you don't work in programming language semantics and so on. So let's try to understand how to read them. So these are inference rules, and you have a line, and you have hypothesis above the line and conclusion below the line. Okay? Let's take probably the simplest one. This says T is an arbitrary type, any is a type any of Julia, and this rule says, no hypothesis, it is always true that a type is subtype of any. Nice and simple. Why should we care about this? Because whenever you write a function and you don't specify the type of the argument, Julia assumes that the type is actually any. Okay? So when now you write foo of 3, Julia knows the concrete type of the argument, it is an int. It applies this rule yes, int is a subtype of any because of that rule, and it will say, okay, 3 is compatible with what this function expects, and dispatch will happen. Another example, if you write foo of hi, then Julia knows that hi is a string, and string is subtype of any because of the very same rule, and dispatch will happen again. Questions until here? Fine? Now, let's move on. Some rules are more complicated. So here we have some hypotheses. So let's try to understand. Let's, again, on an example. Let's take the same function as before, but let's specify that this function expects a number. Okay? And let's now try to apply again, invoke foo of 3. Now, 3 is an int 64. It is an integer. It is not a number. And maybe this rule applies. Okay? Let's try. So here we have a generic conclusion. It says, given a type t and a type t prime, let's take t as int 64 and t prime as number. And let's substitute this inside the rule. What do we get? We get this. Let's just substitute. Progress. But we have two hypotheses that we have to satisfy. The first one says int 64 smaller than t second in TDS. What is this TDS? TDS is nothing more than the user-defined subtype relation. What is that? Well, in Julia, you can define types like, whenever you define a type, like this is a definition of int, you can specify which is the supertype of int, here signed. Okay? So, in the user-defined subtype relation, you have these kind of constraints which are explicitly specified by the programmer. Okay? So, if we replace signed for t second, we get this. Now, int 64 smaller than signed because of what the programmer specified. And we still have to prove that signed is smaller than number. And so we have to go on with how signed has been defined. And for that, we can look at all the subtype relation which is defined by the standard library, which look like this. And any is at the center of the world because everything is subtype of any. And now let's zoom on a little bit of this one. And where is it? Here, we have int 64, number is over there. And we can see that by applying several times this rule, we can go to int, signed, integer, real, number, and derive that int is a number. Fine. Now, this is something that the programmer can completely specify. There are other rules which are implicit in the language. We have seen one, t is smaller than any. Let's see which are the rules for union types. Let's look on an example and the set theoretic interpretation. Is it true that int is a subtype of the union of string and integer? So on the left-hand side, we have the set of all the integers. On the right-hand side, we have the set made by the union of the set of the strings and of the integers. Yes, subtype holds. Why? Because on the right-hand side, we have one type that is a supertype. Okay? So what do we get in this case? We have to solve an exist query. Is there a type on the right which is a supertype of a type on the left? Okay? Now let's take the second one. Union float int smaller than number. Now again the sets. We have on the left-hand side the set of all the floats and all the integers, and on the other side all the numbers. We have to prove, use the set theoretic intuition, that all the elements on the left are actually contained on the set on the right. So this time we have to prove that both float is a subtype of number and int is a subtype of number. So we get a for all check. So there is this asymmetry. If you have a union type on the right-hand side of your subtype query, then you have to solve an exist query. And if it is on the left, then you have to solve a for all query. What if you have in both sides? Well, same rules. You have to prove that for all type on the left, there exists a type on the right that is a supertype. And here it is the case because int 64 is subtype of number, and string is subtype of abstract string. Okay? So, rule of thumb number 2. Union types on the left of subtype have for all semantics, and union types on the right of subtype have exist semantics. Okay? We can write this in mathematical language, getting this root. A union on the left, you have to solve a subtype for all query where you prove that for all the instances, for all the components of the union, subtyping goes. And for the exist, you have to, if the union is on the right, then you have to prove that there is one element of the union that is a supertype. Okay? Now, let's move to the more interesting bits. Vector of integer, vector of any, subtype or not. Let's take the set theoretic intuition. On the left-hand side, we have the set of all the vectors of charts, essentially. A vector where all the elements are ints. And on the right-hand side, we have vectors with arbitrary elements. So set inclusion should work, because the set of the vector with arbitrary elements contains a set of vectors where all elements are integers. Okay? However, Julia wants to go fast. So it will represent vector int as an array of 8-bit machine integer. It is the best representation you can imagine. While vector of any, you don't have the choice. You will have to represent this as an array of pointers to box values because you don't know what you get. So Julia designers made the explicit choice. So this is a design choice of the language to never have representation conversion completely implicit behind your back and to say this should not hold. If you have a vector int 8, it should not be automatically compatible with vector of any. You should do some magic to convert so that you are aware of what's going on. Okay? So what you get is that this does not hold. Okay? And you get inclusion subtype of constructor of parametric types only, we call it when you get invariant type in PL. So imagine that you have name t smaller than name t prime. You have to prove basically that t and t prime are equivalent, which means that t is subtype of t prime and t prime is subtype of t. Okay? So the question is, does this mean that t and t prime are equal? More or less, but imagine union types. The order of the elements doesn't matter. So you don't really want equality. You want really you don't want syntactic equality, you want semantic equality. And the way to express semantic equality is they are both subtype one of the other. Okay? Same. Not sure. I'm sorry. Not sure I got the question. Can we talk about it offline? Do you mind? Yeah. And you have abstract type inside. Still, you have to prove the same. You must have abstract strings in both sides. Otherwise, subtype won't hold. Really. Design choice. If you want to know why this is important for speed, check out nice talk which will be in 2 hours in room, Engineering Julia for Speed, that will explain why this design choice gives you an efficient runtime. Now, the tricky bits. Imagine that we want to define a function over all the signed integers. We can express this using union of all the, we want a function over all the vector of signed integers. We can use union to represent it, okay? At Julia, this is very verbose and can get very hard to read. Julia gives you a very nice construct to express the very same thing, which is the where keyword, okay? So I can express the very same dispatch mechanism, the very same dispatch logic by saying this function will accept any argument whose type is a vector of some type t, where t is a variable, provided that t is smaller, is a subtype of sign. Okay? So let's think about dispatch in this case. We have our function that accepts all the vector of t where t is signed. Hello? Hello? Okay, so let's think that of the function foo that accepts a vector of t where t is smaller of sign. And let's apply it to some argument. Foo of one array of integer. Okay? Now, what we have done, this is just a compact notation for a union we have seen. Okay? So what do we have to do? Imagine that we want to build a derivation. We want to prove that a vector of int64 is a subtype of vector t where t is smaller than sign. Well, it appears on the right, so it is an exist quantification. Let's pick up a type t, and let's see what happens. So if we pick up int as type t, and we substitute int for all occurrences of t, what do we get? We have to prove that int is subtype of signed, which is true, and we have to prove that vector int is subtype of vector int, which is also true. Okay? So the key point to understand this is that if you have a where, a construct on the right, well, you have to pick up an instance of the type t so that subtyping goes. And we can write this informally using a rule that says, a type t prime will be smaller than a where type, provided that I can pick up one t second that satisfies the bounds, such that the subtype relation where I've substituted the type that I want actually holds. Okay? So, if you have a where type on the right of the subtype sign, we have an exist query, like we had with the union types. Okay? You see? We get exist, exist. In one case, we pick up one element in the explicitly given union. On the other case, we have to pick up one type out of thin air. We don't know which one. We have to invent it and prove that subtyping goes. But the quantification is the same. And guess what? If you have a union on the left, it is the same. Same analogy. For union types, we had a for all. And here, we have a for all quantification, as you would expect. Okay? Now, here you have to do two difficult things. You have to pick up an exist type out of thin air. And when you have a for all, you have to prove that for all types. Now, I won't give you the real rules, but I want to show you how the Julia algorithm proceeds so that you have an intuition about what goes on to solve this for all and exist queries. So let's simplify a little bit our example. Vector int smaller than vector t where t. Okay, the first thing that Julia does is says, let's take this variable and let's put it in an environment. Let's recall that this variable t has been introduced with some attributes. Let's look at those attributes. What do we have here? We have variable variable name, easy. We have, was it introduced on the left or on the right of the subtype operator, of the original subtype query? Because in one case, we have to treat this variable with for all semantics, and in one case, with an exists semantics. Okay? And we have two more things. We have an upper bound and a lower bound. Here we didn't specify anything, any constraint for this variable, so this variable can range anywhere between any and bottom. Okay? Bottom is actually an empty unit. Let's try to build a derivation. This is a constructor, vector int, vector t, so we know that the previous rule, we have to prove that int is smaller than t, and that t is smaller than int, invariance. So let's try to do this. We have to prove that given an environment where t is comprised between any and bottom, int smaller than t. So t has exists semantics, so let's pick up one t so that this holds. What can we pick? And let's pick it cleverly. Let's pick the smaller one that satisfies this. Okay? So what we do, yes, this can be satisfied, but we have to update the bounds of t so that now t ranges between int and any. T cannot be smaller than int. Okay? And now we have to prove the opposite side. T is smaller than int. And in which environment? Which are the constraints? Well, we have to use exactly the constraints that we got before. Okay? Because we have to record that t must be bigger than int. And now again, exists query, we can pick up anything we want, provided that that works. So let's pick up int as an upper bound. Okay, so we have to record that t must be bigger than int and smaller than int. And at the end, we propagate these constraints, and guess what? We have discovered that this can be satisfied by picking up t equal to int. Now, constraints in general can be unsatisfiable. Like this is a more complicated query, so I don't want to detail, but if you start matching things by matching vector t, vector int and vector t, you discover that t must be int, because it is what we have just done. Now the same variable is used one more time between string and integer, and here we get that t ranges between any and string. It must be bigger than string. So the final constraint you get are t must be smaller than int and bigger than union int string, which is clearly unsatisfiable. And this subtype query actually doesn't hold. Okay? This is to give you an idea of what goes on behind the hood. Okay, last bit. If I lost you in the previous 5 minutes, come back now. This is important. Look at this code. Equal, x, t, y, t, where t smaller than number, equal, x, equal, y. Wow. What is doing this? This is defining equality for subtypes of numbers in terms of their representation. Equal is the representation the same? And this is what it is doing. Now let's dispatch this to 3 and 3.00, so between an integer and a float. You're, comparing the representation here would be super wrong. Okay? And the type here is tuple of the argument is tuple int and float. So question, given the rules that I gave you, does tuple int float be a subtype of tuple tt where t is smaller than number? And we can, I won't do it. If you build all the constraints, you get these final constraints which are actually satisfiable. And this is scary because it would dispatch and it is not what you would expect. So Julia developers added one rule, which is called the diagonal rule, that says whenever a type variable appears more than once in your type, then it must be bound to a concrete type. You cannot have a union on the left-hand side. Its representation must be fully specified. Okay? And it will say, so dispatch will fail in this case because the diagonal rule will just fail. This is a super simple and clever idea that belongs to Julia, which is actually tricky to implement and formalize correctly. I It is super important. You must know that this happens. Now, you don't want to build the derivation by hand, because this is error prone. But what we have done, is to implement a reference subtyping algorithm, which is in close one-to-one correspondence to the rules that I showed you directly in Julia. Okay? You can download it, and you can ask queries like this one, which I've seen. And if you are in debug mode, it will output. So it will conclude that true. It will give you the bounds. Int, it is what we got before. It will give you information about the diagonal rule. And especially, it will give you an XML trace, which is not super fancy visualization, but it is actually usable if you are in a, I had it somewhere. Here we go. Not sure it is readable, but it is actually useful here to investigate what goes on, and you can skip all the bits you don't care. It is vital for debugging. You have a trace of what's going on. Okay? Back to the plot. All this was fun, and we found some unexpected behaviors. There were several. I just pointed out one. Okay? Pick up these two functions. Function foo that takes an empty union. An empty union on the right will have exist semantics, exist in an empty set. You will never dispatch to this function. Okay? And let's take the second one. Function foo x takes a tuple of empty union. Again, we have an empty union on the right. We have an exist. You will never dispatch to this function either. So when you consider dispatch, these two functions are really equivalent. However, if you try to prove if you try to prove that the two types are equivalent, then you will fail, because tuple unions of empty union is not subtype of union of empty union. And building on this plus the diagonal rule, we were able to find a counterexample to one of the basic properties we would have expected from the subtype relation, which is transitivity. And there were several. And we were impressed by the design, and the good and the bad. It was nice. So I'd like to conclude with two things. I believe that this work gives two things. Point number one, communication with programmers. You all have a precise and accessible set of rules of the language. You can read it on paper. You can play with the reference implementation. You can check with the simulator what goes on. And, and point number two is validation basically for Jeff and Julia developers. All this enables them to explore the corner cases of the language. And I don't know yet if point one is fulfilled, but I can tell that for point two, from time to time, we used to receive emails like, from Jeff, this is great, somehow staring at your derivations made me realize the problem, and I have a fix. And how to say, these emails made our day. Thank you.
Thanks for a beautiful talk. Any questions?
Are there unit tests which test your reference implementation against the Julia implementation?
Thanks for this question. I love it. You should never trust an academic that sets you a set of rules. Never, ever do it. So the first thing we did, while developing the rules, we developed the reference implementation, which is Julia code one-to-one with the rules, plus a search along the rules. You have to turn the rules, which are a specification, into an algorithm. So there is a search on top of them. And what we did
was to set up some framework to do differential testing of our implementation against Julia subtyping, the real subtyping, which is whatever subtype.c provides. And we test this, of course, on the subtype test suite, which comprises, I don't know, I mean, the original one was 200 tests, which were all bug reports, and we pass all of them. Now there is some more automatic things. We pass all of them, and but we were not happy with this because we realized that there were corner cases which were not covered by the test suite, by the standard test suite. So we instrumented the Julia runtime to log all the subtype queries made when you execute a program. And we took 100 packages, widely used packages from GitHub. We logged all the subtype queries that you get by running the test suite of those packages. So these are really the subtype queries that happen in practice. And we got some 6 million something else subtype queries. And we pass all of them except, I believe, 122. 120 turned out to be a Julia bug. So we were formalizing Julia 06. So in 07 it is fixed. And there are 2 that are big, and we didn't have the courage to look into them.
Any more questions?
You mentioned that there was an exception to the transitivity relationship and that there were a few others you found. Could you let us know what those were?
Nothing you should worry about. Honestly. I mean, once you have these roots, you can start investigating the real obscure corner cases. Whether those occur in the programming practice is another question. So the transitivity thing is not a problem for programming because, well, in both cases, you never dispatch. You need this empty union somewhere. You will never dispatch. Honestly, you don't have to care about those as a programmer. There is another one, which is an interesting one, which is when you update the constraint in some complicated case, Julia developers had a very nice intuition that updating those in some particular way, in some simple way, was good enough. And it was a counterexample, and recently, a few months ago, Ross8 and our Julia actually found a counterexample to those updates of constraint, and you actually need to compute intersection types to update those constraints correctly. Again, examples are not something that would happen in the programming practice, and that's probably why never it has been in the code since the very first version of Julia, and was never a problem in practice. And it is now computing intersection types to really fix the problem is super hard and super slow. This has been fixed by adding a simple intersection a simple function that computes intersection types in the common cases. So in all the common cases that reasonably happen in the programming practice, you will get the correct rule. And
so if I understand you've correctly, you've developed a formal description of the set of subtyping rules. Do you also have essentially, so you found an exception to transitivity. Have there emerged sort of invariants or properties that are like transitivity that you can prove that we do or do not sort of satisfy those? I mean, or stated conversely, is there a set of axioms from which you could progress and essentially derive what Julia's type system rules are?
Yeah. Can I say future work? Honestly, the rules are still the system is still reasonably complicated if you try to do formal proofs with them, and even proving that
the order of the arguments in the union type doesn't matter. It's not super trivial because the way our constraints are propagated after each match. So, I mean, it has to be done. It is not super simple. Julia and Artyom and Ben, I believe they are working on a more abstract view. I mean, the rules that I gave are really a description of the algorithm, except that the recursion is simplified. The two stacks, we use a different search. Julia, Ben, and Artyom are looking for more abstract rules, but it is an art task. But I believe that if you want to actually prove properties, you first must derive more abstract characterization of these rules before you can actually prove things about it.
Can you replace 2,000 lines of C with Julia now?
It is super slow.
Okay, well, thanks again. The next session is at